Okay. Hello, everybody. Just testing if you guys can hear me. Let me know in the chat if you can or if you can't, or if it's too loud. You can hear. Amazing. Thank you so much. Oh, is that Henry? That's Henry. Epic. Who's here to set us off. Cool. Okay. Oh, there's an echo. Um, Let me turn it down a little bit. Sorry, I'm not like Tech Henry. I'm not super cool and don't have a massive streaming setup, so I'm hoping my AirPod mic is okay and it's not too bad. But let me know at any point in the chat if it becomes too bad, and I'll like see what I can do. But yeah, hello everybody, and welcome to week 7, lecture 2. Link list. That's pretty much all we're going to be looking at for today. Super stoked to get into it. I guess we'll just jump straight into a little recap of what we did in yesterday's lecture, and then we'll go even further into some more linked list stuff. So hopefully you guys remember all the stuff we did with multi-file projects yesterday, and we threw together this little program together. So multi-file projects, if you don't remember, are a super cool way to move our program into separate files that are a little more modular, easier to read, and just make it easier to navigate a bit more complex code bases. So we have this one here that we made. So remembering we have a main.c that contains our main function. And inside of our main function, we are having the entry point to our program, and we're trying to make this like as small as possible and not put much in here. So right now, this is not an overly great main function, but we will get there and we will refactor this today as we do a lot more with our linked list implementation. We have our header file, which creates all the documentation. So think your enums, your constants, your function prototypes, or your function comments, things like that. And then our implementation file. So that's going to be containing all the implementation for all the functions that you're going to be implementing. So that's kind of the first bit of things that we covered yesterday. We also did a recap of memory, and then we started looking at what a linked list is, but we're going to dive into that a ton more today. And let's take a look. I'm going to flick right through so we can remind ourselves what a linked list is before we go into inserting. Here we are. So for those of you who don't remember, linked lists, remembering they're a dynamically sized data structure, which let you link a bunch of nodes together in a list-like format where they're all pointing to each other. So the key characteristic of a linked list node is that it has this thing called a next pointer. And this next pointer is a pointer to the next node in the list. So you need to follow it like sequence, like what we have here, where we have the node containing data 3, pointing to the node containing data 5, pointing to the node containing data 1, which then points to null. So remember that these are not like an array, because an array is one continuous block of memory. And in this continuous block of memory, we can access it by index, right? You can go index 0, index 1, you can go straight to index 4 if you want to, and you know exactly where it lives, whereas a linked list, we can only traverse it from the start to find the very tail of the list. So speaking of these terms of like start, tail, and node, for those of you who may not remember, a node is what we call like each little thing in our list, and it contains some data and a pointer to the next node, and this is what forms our list. So right here, this one has a integer, and that member is called data. You can have characters, doubles, strings. You can really have anything, and you can have any combination of things. So a linked list node doesn't strictly need to contain just an integer, and you'll see this a lot in assignment 2, for example. And then, like I mentioned earlier, we have this struct node pointer next, which is a pointer to the next node in the list, and this is critical for a linked list. We kind of spoke about this yesterday, but again, the head pointer, this is the pointer to the first node in our list. So we call it the head, it's just the, I guess, colloquial technical term, whatever you want to call it. but it just points to the first node in the list so we can keep track of our entire list. Because remember that unlike an array, I can't access whatever's at maybe the second or third position in the list. I need to get there from the first node in the list. But we need something to keep track of this first node so we know where our list starts. And to do that, we use a head pointer. The other little bit of terminology that we learned about yesterday was the tail node. So this tail node is basically just the last node in our linked list. It just has a special property that it points to null. So its next pointer does not contain some hexadecimal memory address of the next node in the list. Instead, it points to null. I will just call out again that this null basically means nothingness. It is not the null terminating character. Yeah? So it's slightly different. And then we kind of end up diagramming linked lists looking a little bit something like this. So we kind of ended up stepping through the linked list yesterday and kind of building one together. So we're going to go through the code that we went through yesterday and we'll just diagram it and talk through what's happening at each point. Because remember, diagrams are your best friend when you're working with linked lists. And while we do this, if we can just have a poll, lecture moderators, please, just asking how students are feeling about the general terminology and concept of what a linked list is, that would be amazing. Thank you, team. So let's go through this code we wrote yesterday and diagram it out. And we can take a look at it all and make sure we understand everything before we keep moving. So I'm just gonna split screen this really quick so we can see the code, and we can also hopefully see a diagram. Okay. We'll hop over to main.c and follow this line by line and take a look at everything as we go. So let me just check that this is going to work. Scroll up a little bit on this whiteboard. Perfect. Okay, so the first thing we do here on line 7 of our main function is we are creating a head pointer that will point to the head of our linked list. But right now we're going to set it to point to null because we haven't created the list yet. So diagrammatically, that just looks like we have a head pointer and that is pointing to null. Yeah? And the next thing we're doing is we're letting this head pointer equal to a new node with data 1. So let's take a look at our create node function so we can see what it's doing. So this function create node returns a pointer to a new struct node, and it takes in some integer as its parameters. So here we're creating a new node. So we're creating something called new node. Let's do new node. And this node is of type struct node. And looking at list.h, we can see that a type struct node contains some data field and also a next pointer. So let's set that up. It's going to contain some data, that's going to equal something, and we have a next pointer. And that next is going to equal something. So we've malloced enough memory for the size of this struct node in our heap. So remembering that by using malloc, this memory is now allocated to the heap in the computer rather than a normal variable which exists on the stack, which means that when I return the pointer to this new node, this variable will still exist because it's stored on the computer's heap. So it's not scoped to the stack frame of this create node function. So we've created our node and we let the new node data field equal to number. In this case, I think we called it with, was it 1? Yeah. So data is going to equal to 1. And we let new node next just point to null right now. Now, this notation here, if you remember, is equivalent to how we dereference a struct and then access the member. So normally, if you wanted to dereference a pointer, you would use this. Ooh, my IntelliSense is interesting today. I think I might have some AI tooling on that I will quickly turn off after we go through this. So we have a dereference here. So if I did something like, I don't know, my number, this would mean that we are dereferencing the pointer to get the value of it. So we need to dereference the struct, but because we have a struct, we also need to access the member. So we use the dot notation. So for a struct, we would need to dereference new node and then access it. And we can do this to access the data field, but it is a little bit hard to remember to type all of these things. So that's why we have our shorthand stab notation, which we can use to access and dereference a struct pointer. So it's the same thing there. So we've accessed the number field, we've accessed the next pointer, and then we return this to our main function. So coming back to main, we're letting head equal to the return value of this function, which means that our head pointer, which previously pointed to null, is now going to point to new node. So instead of pointing to null, head now points to this new node that we created. And this is no longer a new node. Yeah? Cool. Thanks for the poll, lecture moderators. Okay, so the next line of code is we're creating another node with our create node function, and we're assigning the return value of this function to a new pointer called new node. So if we just, let me just swipe over here. We're creating, here we are. We are creating a node and remembering that we're calling our create node function. So we're mallocing enough space for a struct node. It's going to be called new node. And we have a data field and we have a next pointer. In create node, we let next point to null and we let data equal to the number that was passed in. So in this case, we pass in 3. So we let that equal to the data field of our new node. So now that we've got this and we've returned it to main, it's known as new node, and we let new node next equal to whatever head currently points to. So new node, which is this one here, its next member needs to point to this node over here. So it's no longer going to point to null because we can only point to one thing. So instead of pointing there, it's now going to point over here. And we can now see we've got a little bit of a chain going on, but we need to find a way to connect everything up because head points to here, which means right now our new node is not reachable. So to make our new node reachable, we're letting head point to new node. So we're going to be updating this pointer to point over here. So our list will follow new node, then it will point to 1. So we'll have 3 followed by 1. Now, the reason, if you remember yesterday, that we update our head pointer after next is because if we didn't do it in this order and we updated our head pointer first, we would lose the memory address of the old head if we just made head point to our new node. So we need to make sure that we don't lose any connections in our list. So we're updating our pointers in the correct order. Cool. So the next thing we do on line 16 is we create another new node and we're calling our create node function again. So let's create another node with malloc like we do in our function. And this one is now called new node. And in our create node function, we malloc enough size for a struct node. We let its data field equal to 5, and we let its next pointer point to null to begin with, and we return it to our main function. And now that we've got this new node back in main, we want to connect our new node to the rest of the list. So similar, let me just move my diagram over. Cool. Similar to what we did before, we don't just want to go ahead and update this head pointer straight away, because then we would lose both of the memory addresses of the other two nodes in our list. So we go ahead and we update our new node next to point to the current head of the list. So then we can redirect our head pointer to the new node, which is what we're doing in our code. So let's go ahead and do that also in our diagram so we can see it there. So we let the next pointer point to the current head of the list, and then we update head to point to our newest node. And now we've built a very, very basic linked list by doing what's called an insert at head operation. The last thing we're doing down here on line 20 is we are calling a print list function. So let's take a look what the print list function is doing over there. So print list takes a pointer to the first node of the list as the parameter, and it doesn't return anything. So all that print list is given is the memory address of like this first node here. And we're going to be traversing our list to print the data field of each node in the list. So to do this, we use what's called a current pointer to track our current position in the list. It's just an iterator similar to how you might use like I or J or row or column, but it is a pointer to a struct node. So we create a pointer, and this pointer variable is going to be called current, and it's going to point to whatever head points to in our list. So in this case, it's our first node here with data value equaling to 5. So I'm just going to turn the light on. There we go. Okay. So now that it's pointing to our data node with 5, we can go ahead and go through our linked list until the end of the list to print the data field for each one. So we use the condition while current does not equal to null because we know that that is the special property for when we're at the last node in our list, or just past it, I should say. If we did current next equals to null, our while loop would stop when current points to the last node in our list. But in this case, we want to look at every single node in our list, not just stop at the last node. So we want to stop while current is pointing to this null over here. So while current does not equal to null, we print the data. So in this case, data is 5. So we would like print 5 to the terminal per se. And then we move current along. So we say current equals to current next. So that means that current, this pointer here, equals to whatever current's next pointer is. So we follow that connection along there, meaning that current is now going to point to the next node in our list, this one over here. And we call our printf statement, and it will print whatever the copy is there, but it will also print a 3. And then we go again to our loop. Current equals to current next. So current, and we follow the current next connection, which is going to take us over here, meaning that this pointer is updated to point to this node in our list. And then we check our condition. Does current equal to null? Well, no, it does not. So we continue with our loop. And we print the data. So we access current data and we print it out. So this is 1. And we go current equals to current next. So current, we find its next pointer, which is this one over here, meaning that current is now going to point to null. So we remove this pointer here and override it to point to current next. And we check, is current next equal to null? Well, in this case, it is, meaning that our while loop condition has now been met. So while current is not equal to null. And because current is pointing over here, we no longer continue with our loop and this function ends, and we've printed all of the elements of our list to the terminal. So I'll just pause there for a second to see if anyone has any big questions, queries, concerns, complaints, or comments before we move on to formalizing inserting at the head And while I do that, I'm just going to very quickly uninstall this. See if it's still shouldn't it's still working. Gonna quit VS Code. Oh, move my camera. Yes, of course I can. Sorry, I didn't realize I am on top of the diagram. Give me 1 second. There we go. Think it shouldn't be in the way now. Oh, there's like a little black thing. There we go. I think that's better. And then when we code, I will make it really, really small. Let me just open up VS Code again, and hopefully removing that extension has made everything work. I'm just looking at the chat. And of course, I can give you guys a link to the whiteboard live. Just give me 1 second. Anyone at UNSW? And I'll just pop this in the lecture chat for you. Perfect. Okay. And then let me just open up my SSHFS because everything just died on me. And then we should be good to keep going. Okay. Looks good. So, now that we have recapped everything we did yesterday, what we're going to be doing today is we are going to not be saying thank you. The lecture is not quite over yet. We're going to be formalizing all of the ways we can insert into a linked list. So that will mean inserting at the head, which is what we just went through, inserting between any two nodes, and inserting at the tail of the list. So let's formalize insert at the head a little bit more before we move on, and then we will do the other two insertion methods. So I'm going to make this one full screen here. And when I say formalize it, hopefully you'll have realized that these chunks of code, so creating the node and hooking up the next pointer and redirecting head, these are two very similar things, right? This is a bit of repeated code, and we shouldn't have repeated code. So let's create a function called insert at head that will insert a node into the head of our linked list. So let's pop over to list.h so we can define the function. So function that inserts, oh no. Oh, Microsoft is AI now. Everything is AI now. Inserts. I'm just gonna quickly uninstall anything that might have a little bit of AI. Because we don't want any of that when we're learning, because then we don't get to learn ourselves. Save. No. Close. Don't save. Sorry, 1 moment. I did test this before, but apparently it doesn't like it when I'm live, which, what's new? There has to be some technical difficulty, otherwise it would be too smooth and too easy. Okay. Third time's a charm. If not, we can go back to the good old days and we can use like a text editor. But I really don't want to do that because it will make everybody's eyes bleed. So I'm trying my best. Or targeting NC maybe. Okay, third time's a charm, everybody. That instance node. Okay, Tiger VNC it is. Here we go. Sorry, everybody. I think it's something with my local. And this is now gonna be what's gonna happen. One minute while I log in. Okay. Here we go. Public HTML lecture code 2062. And let's go to week 7. Lists. And we're gonna open that up. Okay. Why is there AI here now? Yes, I trust. Let me in. I trust myself, I promise. I'm trustworthy. Okay. Wow, I haven't opened this in a good while. How do I? Okay. Go away. AI agent, go bye-bye. Terminal. New terminal. Okay. Sorry about that, everybody. Hopefully you can forgive me. And I will bring our list.c and list.h for now here. Okay, perfect. We're back. So we're writing a function that inserts a node into the head of a linked list. So this node, if we're going to be updating the head pointer at every point when we're inserting into the list, we're going to need to return the new memory address that is the head pointer. So it's going to return a pointer to a struct node. So struct node insert at head. And this, and my IntelliSense works now. This is great. This is going to take a pointer to the current head of the list because we're going to be updating it. Struct node head. And maybe we can also call create node from this function. So let's pass it the number. So now we can implement this in our .c file where all of our actual business logic and implementation goes. So we have struct node, I can't type, struct node insert head, and we give it a pointer to the head node of our list, the old head, and we give it the node we want to insert. So the first thing we're going to need to do is taking our code from main. We're going to want to create the new node and then insert it. So we can do struct node new node is going to equal to create node. Create node, and we pass it the number that we want to be the data field of our node. And now that we've created this node, we can go ahead and insert it into our list. So there's a few things we usually need to consider when we are inserting into linked lists. Some base cases, edge cases, things like that. The main two for right now that we can think about is what needs to happen when our list is already empty and we're trying to insert a node and it's going to be the first node in our list. And then we need to consider what happens if I already have nodes in my list. So let's take a look at them diagrammatically and see if we need to handle them any differently in the code that we are about to write. So I'm just going to move this over here. Okay, and come over here. So if we have a node, a linked list that is already empty and head points to null, and I've gone ahead and created some new node with a data value of 1 and it points to null. Oh, sorry. And my head is again in the way. I'll move over here. Is there anything that I need to do particularly if I want to insert this at the head? Or can I just go ahead and update my head pointer? Any suggestions from the chat? I feel like there's a lag. Or no one wants to answer me. I can't tell. I'm going to assume it's a lag, so I'm going to keep talking and hope that messages come to the chat by the time this reaches y'all. But we can just go ahead and update our head pointer to point here, right? Because it's an empty list, there's nothing we're going to lose if we update this head pointer. So we can go ahead and do that in our code. So we can go head equals to new node, and then we can go ahead and return the head pointer. Now, this is all well and good for this case where there are no nodes in our list. But this might not work when we have multiple nodes in our list. So let's think through that case now. So if this has worked and I have a head pointer, let's say it points to this node because that's what I inserted. If I go ahead and call this function again and I create another node, let's say it has data of 7 and it points to null, updating this to point here is going to lose this node, right? We're going to lose track of it. We didn't even call free. So it's just lost in the computer's memory. So exactly like Oliver suggested in the chat, we need to make sure that we update the next pointer of the new node to point to the existing head, and then we can update this. And if we think about it, the existing head was null for the case that we only had, for the case when we had no nodes in the list. So that will work for both cases, and we don't need to do any if statements to handle this right now. So let's go ahead and update our insert head function to make sure that we're doing new node next equals to head, and then we can update head to point to the new node in the list. So now we can set head equals to null, and instead of doing all of this, I guess for right now, all of this what we have here, we can go insert at head, and we want to pass it a pointer to the first node in the list, and we also want to pass it what we want to insert. So this is 1. And now this chunk here again, really simply, this can just be refactored to call our new insert at head function. Also, I probably should have made a copy of my lecture code before I modify it from yesterday. So I'm just going to very, very quickly do that before we continue. And I'm just going to quickly CP everything over so I don't affect any of the code from yesterday if anyone wanted to look back at it. Just give me one moment. Week 7. CP-R list lec1. Cool. Okay, there we go. So we'll keep working in the same file, and we will continue doing this. So we'll go head equals to insert at head. We give it the first pointer, the pointer to the first node in our list, and we also give it the number that we want to insert. And we can finally do the same thing for our other node that we have. So head equals to insert head. We pass it the first node in our list and the node we want to insert. So now hopefully when I compile this, list.c main.c -o list, hopefully it compiles, perfect. Oops, okay. So my camera's like right in the middle of my screen, so I need to look around it. But we can see that it inserted into our list 5, 3, 1, because we insert 1, then we insert 3 in the head again, and 5 in the head in front of it, similar to exactly what we diagrammed earlier here, right? And it printed 5, 3, 1, which is exactly what we expect. Any questions about how we insert at the head? If you do, pop them in the chat and our lovely lecture moderators, I'm sure, will help you out. And we will continue moving on to another insertion method, which someone suggested we do yesterday in the lecture. Just move myself there so I don't cover the compiling command. And that is going to be insert at tail. So up until this point, we've only inserted at the head, which is great. But what if I want to insert something at the end of my list? So let's have a think about what we need to do if we want to insert at the end. So for linked lists, because we can't access all the nodes up front, we don't know how big our list is, we don't know what is currently in our list. So we're going to need to find the last node in our list and stop at the last node so we can insert after it. So we know that the last node in our list is the node that's next pointer points to null, right? And that's this node here. So we want to insert some new node with some data value that's going to point to null over here, right? And that's kind of what we want as an end state. Ooh, did my Wi-Fi drop out? Am I frozen on the stream? Oh, great. Okay, I can see someone has put it in the chat. I'm going to assume the stream is okay. I just saw a little warning sign, but I think it's okay. And yeah, we can see someone has put a suggestion in the chat to look at the condition. Oh, perfect. Thank you, Bella. While current next does not equal to null. So someone suggested we do this, which is exactly correct. We're going to need to traverse our linked lists till we find the node that's next pointer points to null, aka this blue pointer here, and then we're able to call our create node function and insert that into the list. So let's go ahead and implement that in code. So let's create a function prototype in here. So function to insert a node into the tail, probably not into, at the tail of the list. And I didn't do it last time, but I should write out my parameters. So we'll do parameters, and it takes head, which is a pointer to the head of the list. This one's also going to take number, which is the node data we want to insert. And we will have returns. And this one, we're also going to return the head, which we'll get to why in a little bit when we consider a few of the cases. So struct node insert tail. And similar to this here, we want this, oh, what just happened? Okay, we want this and we want to pop it in here. Perfect. Okay, so we're also giving it the head and some number. Let's go ahead and implement it. Control C. We don't need these comments. You can have them, they're optional. You should at least have this though. Okay, so insert at tail. So we need a current to track and traverse because we need to be checking this condition, right? So let's go ahead and create a current pointer. So struct node current is going to equal to head, which is the first node in our list. And while current does not equal to null, oopsie, we want to keep moving along our list, right? Because we want to traverse it till we find the last node in the list. So while current next does not equal to null, we just want to do current equals to current next. And at this point, when our loop has ended, our current pointer is going to be in the position of this blue pointer here. And we would have reached the last node in our list. And at this point, we can create the node and make current next point to the new node, right? Because currently at this point, current next is this here. And we want to create our new node and append it to the end of the list. So we will call create node to make this section here. And then we can do current next equals to new node, which is going to create this pointer here and allow us to have a list with the nodes and follow the connections like so. So let's go ahead and put that in our program. So we will go struct node new node equals to create node. And this is why we created our create node function, right? So it's super easy every single time we want to create a new node in our list, and it's super broken up between all of our helper functions. So this just takes the number which is fine. We can pass that in. And now that I've got this new node, we want to add it to the end. So we can do current next is going to equal to new node. And even though right now I didn't modify it, let's still return the head of our list. So let's call this function in main. So we can go head equals to insert at tail, and let's insert -1. It also takes head. And let's compile our program. And run it. And we expect the list to be 5, 3, 1, -1. Because we've inserted 3 nodes at the head and then 1 at the tail, which works. Now, there is one edge case that we need to consider for inserting at the tail. Does anybody have any ideas what we might need to consider, or what might happen if we have different states of a linked list and we call insert at tail? So the hint is if I commented out all of this here, yeah, exactly. Someone's popped that in the chat. So if head is null. So let's give our code a try and see what happens if we're trying to insert at the tail and it's the first node in our list. Oh no, we got a runtime error. That's not good. So we've got this runtime error saying we're trying to access a field via a null pointer. So what this means diagrammatically, because diagrams are your best friend with linked lists, what that means is that you've got head, which points to null, and in the code, the first thing we do is we check current next. And if current points to head, do we have a current next right now? Is this a struct node? Well, no, right? It's null. It is not of type struct node. It does not have a next pointer that you can access and check in your while loop condition. So we need to do what's called edge case checking, and we need to check if the list is empty. And if the list is empty, we just want to create our node and return that as the head of our list, right? Because we don't have anything to traverse to find the tail of our list. So we can just, in this case, create the node, have it point to null, and we just want to update our head pointer to not point to null and just point to the new node, rather than trying to traverse in a list that does not exist. Yeah? So let's pop that into our program. So once we create this, we can do something like if head equals to null. And what do we want to do? Well, we want to create our new node and we want to add it to the head of the list. So if we always are going to want to create the node, it might be worth, oh my gosh, why is everything clicking? Hello? Sorry, I don't know what just happened. It might be worth moving this to the top of our program instead of putting it here, since we always want to do it. So let's paste that there. So the first thing we do is create our node. So if head, why is tab? Okay. If head equals to null, we can just let head why is my whole keyboard not working? Why is the wall against me? Have I locked control? Okay, there we go. Sorry. So if head is null, we want to let head equal to the new node in our list because we just want to insert it there. And then we can just go ahead and return head because we can return early because we don't want to traverse our list. If we try and do that, we're just going to get a runtime error and things aren't going to do what we want. So let's just return head now and be done with it. And then if we have elements in our list, we can go ahead and try and traverse our list to find the end of our list so we can insert a node there. So now let's compile it and see if it works with our adjusted main function that does not have anything before calling insert tail. And no, it looks like it works, which is great. And if we add these back in, we can check that it works for the case that we have nodes existing in the list as well. And we can see that also works as expected, which is really great. I'll just pause for a minute. Can we please get a poll asking if we want to go through insert at tail anymore? And while we're running that poll, I can see a few questions in the chat about a few different admin related things. So I will just draw your attention before the lecture break to a few things. So remember that in week 8, as your checkoff, you'll be completing a mini exam, which is an array hurdle and some debug questions, and you get to try the exam environment and give it in timed conditions. So if you are an online student, meaning that your Tute Lab takes place on Microsoft Teams every week, please make sure you sign up to attend an in-person session in week 8. This link will also be posted on the forum. We'll also have our week 8 revision sessions, so you can sign up for those, and I believe those have also already been posted on the course forum. And there are a few questions in the chat about assignment 2 and when that is releasing. So assignment 2 is a multi-file linked list project that will be releasing tomorrow morning for you, and we will post details of that on the forum. Okay, so there are a few people that want a bit more insert at tail practice. So let's go through our code line by line and diagram it out. And then we will take a lecture break and do a Kahoot and come back to do insert at nth. So let me get a better split screen so I don't have to flick between the two every minute. Can I draw in targeting C? Perfect. Okay. Insert at tail. Get a clean whiteboard. So let's take a look at the case of if we have a list with 3 nodes in it. So we have this list with data points 10, data point, 15, and 20, and this points to null. And we have a head pointer for this linked list. So this is the list we've had, and then I've called the insert tail function with add pointer and some number. Let's say I want to enter a node with value 5 into my list. Yeah, and that's what I've called my function with. So the first thing we do is we create a current pointer, and this current pointer points to the head of our linked list. And this current pointer is our iterator that we're going to use to track our current position in the list as we move through the list to find where we want to insert our node, because we can't just go, oh, yeah, I know I want to insert my node at position 4 or something like that. We also then go ahead and call our create node function, which mallocs some space for a new struct node, allocates the data that we pass to it, so it has a data field of 5, and it has a next pointer, which points to null. So it's just a lonely little node sitting in our computer's heap memory with no friends and no list friends next to it. It's all alone and sad. So we want to link it up to the rest of the list, which is what we go ahead and do. The first thing we do on line 38 is we check if head is null. So we check if the list is empty. And we can see here that head points to some node, meaning that it points to a hexadecimal address in memory and does not point to null. So we skip this and we go straight to the while loop, where we're going to be traversing our list to find the last node in the list. So we check while current next does not equal to null. So while current next does not equal to null, and in this case it points to a node, we do current equals to current next, meaning that we move this pointer. So this current pointer equals to current next. So we're going to update it to point to the next node in the list. So current now points to the node with value 15. And we check again. Is current next pointer equal to null? Well, no. In this case, current next points to the node with data 20. So we do current equals to current next, moving current next to point to the node with value 20. So let's update our pointer here. And then we check again. Does current next equal to null? Well, in this case, current next does in fact point to null, meaning that current is pointing to the last node in our list at this point in our program. So at this point, we don't want to keep traversing because we don't want to exceed our linked list. We want to stay pointing to the last node so we can attach our new node to the end of the list, which is exactly what we're doing on line 47, where we say current next. So this pointer here is now going to point to new node. So instead of pointing to null, the node with value 20 is now going to point to the node with value 5. So we overwrite this pointer to point here, and then we return the head of our list because we always need to keep track of the head and we don't want to lose it. So it's generally a good thing to make sure we're always returning from functions. So that's how our insert at head function works if we have nodes in our list. If we have no nodes in our list and we're calling it on an empty list and we just have a head pointer that points to null, the first thing we do is that we set current to point to the same thing as head, which in this case just happens to be null. We then go ahead and create our new node with our data field. So we call create node, which mallocs some space on the heap. We set the data field and we make that node point to null. And then we check, is head equal to null? In this case, head does point to null, right? It doesn't point to a hexadecimal address. We don't have a list. So we enter the if statement and we let the head pointer point to the new node in our list. So instead of pointing to null, head now points here, which means that by effect, actually, no, current points to the old head. So current still points to null. Current doesn't point to our new node because it's set, right? It doesn't dynamically change as head changes. So head points to new null, and then we go ahead and we return head, which means we return the memory address of this new first node in our list on line 40. So this is kind of showing us that when we're working with linked lists, we always need to think about what if I have nodes in my list and what if my list is empty. An empty list check, this if head equals to null, is something you should basically do in almost every linked list function that you write. If we think about it and extend this, would our print function, like it would just go ahead and print nothing right now if we had an empty list, right? Because if we had the empty list with head pointing to null, it would just skip this loop and print nothing. So we should probably also add a if head equals to null. We want to tell people that the list is empty instead of just printing nothing. So we can do printf, the list is empty. So it's a case that we should realistically always be considering when we are working with linked lists. Hopefully that makes insert tail make a little more sense. We will go into a 5-minute break. So have a think about it, have some water, have a little break, and see how you feel. We'll pop another poll about how you're feeling about inserting a tail and kind of what a linked list is over the break. We'll come back, maybe do a Kahoot, and we will take it from there. Just find the thing. Okay, so we're back, and energy's a little low. Apparently, my lighting is also low. But I think it's Kahoot time. Let me know if you can't hear the Kahoot music, because obviously that's the most important part of today's lecture, and I will try my very best to fix it. But yeah, join up on the Kahoot. I don't know what's going on with my lights. Let me turn some lights on. Whoa. Okay. There we go. There has to be more than two of you on this lecture. And I have word from Henry. He's promised Pokemon cards to the winners. So if you win this, make sure you maybe keep a screenshot or remember that you won the Kahoot, and you will get Pokemon cards when Henry returns. Because obviously we're all in it for the Pokemon cards. I want to play. I want a Pokemon card, but I don't think I'm allowed. You can't hear the Kahoot music? Okay, let me try something. Can we hear the Kahoot music now? Oh, I want this. Oh, did it just nuke everyone out as I did that? Sorry. Please rejoin. My apologies about that. I got told I should have a setting that I just added. Also, I don't think you can hear the Kahoot music, which is really sad. Unfortunately, I'm not as cool as Henry, but I can try and make it work by doing this. If I can, I'll pay it out of YouTube on my phone into my AirPods, because that's technology at its finest, everybody. While you all join. It won't be synced, but we'll still get the vibes. Okay, I think we've got a fair few people on here. And I've got my 10 hours of Kahoot music loaded in. And hopefully you can hear it. Let's go. Okay, not too bad. For those of you who aren't feeling super confident, hopefully with this week's tutorial we'll get a bit more confident with pointers. Also, I think I fixed the settings. Okay, so yeah, on this one here, what we're doing is we are defining a pointer variable and assigning the value to it all in one line. So you don't need to define a pointer and then dereference it to assign the value in separate lines, just like how you can declare and initialize a variable in one line, a regular variable, you can do the same with pointer variables. Very good. So it looks like the majority got it, and that's exactly correct. A pointer is a variable that stores the address of some variable in the computer's heap. Very good job. Okay, so we want to access the value or dereference a pointer. And to do that, we use the asterisk. The ampersand is used to get the address of some variable if we wanted to maybe assign it to a pointer variable. Okay, this one is a little bit tricky actually, and it's something that I didn't cover in my lecture yesterday, and I hope Henry covered it in his, but if not, let's do a little recap here. So we are declaring and initializing an integer array of size 3 and storing the elements 1, 2, 3 in them. For this one, I might actually pull out a whiteboard. I hate to break up the fun of a Kahoot, but let's go ahead and just diagram this one real quick and chat through what's going on, because it's a little bit confusing and one of the quirks of C that I think are actually really interesting. And we have time. So we have this, and we have some array, and this integer array is of size 3, and the elements in this array are 1, 2, and 3. Yeah? So then we go ahead and we let some pointer variable equal to the memory address of our array. So it might be like OXFFA something something something, right? But the interesting thing is that every single time that you have been accessing an element in an array, so say you go to the array at index 0, you are accessing the memory address and dereferencing basically a pointer to access what is at that element in the array to get you 1. But this here is basically under the hood being like, get me whatever is at OX FFA. And then when you do something like accessing the element at array 1, what that's doing under the hood, besides just giving you whatever's at that index 2, is it's getting the hexadecimal code of the start of the array and adding like an offset to it. So the offset is whatever you've put in the brackets here. So this will be like 1 times the number of bytes to move along in the computer's memory. So in this case, integers, so like 4. Well, it corrected my 4 to a triangle, sorry. 1 times 4, and it will add that to the offset to allow you to access allow you to access what's stored at that memory address, which just so happens to be in a continuous block of memory. So it's all kind of crazy that you've really been using pointers under the hood. And this is kind of why in assignment one, you might have noticed that you can pass an array into a function and modify it without needing to return it, because you've been modifying heap memory. And how arrays kind of work is that it's like, yeah, pointers under the hood-ish, if you had to oversimplify things. So that might answer that question of like, why can I pass an array into a function and not modify and not have to like return things, and it can just be modified. So that's really cool. And that means that by doing what we've done here and just printing %d of a dereferenced pointer, what we're doing is we're basically dereferencing whatever is at array of index 0, because pointer points to the first, to the memory address of array, which is like the first element in the array, because it's got a 0 offset, if that makes sense. It's a little bit confusing. You don't really need to touch it too much in this course, but it's something really cool with memory and how arrays work in C that you can dig into. I strongly recommend asking your tutors more about this in your labs this week if you're curious a little bit more about how this works. But I will stop holding you all from your Kahoot, and we can keep going through with Kahoot music, of course. Okay, so most of you got this as 5. So what this piece of code is doing is we are declaring and initializing an integer variable called a that stores the value of 5. We then declaring and initializing a pointer called p, and it's going to point to the memory address of a. So p is pointing to the variable a, and then we're printing the dereferenced p. So that means that we're going to get the value stored at the memory address of whatever p points to. So if p points to the memory address of a, we're going to dereference that address, which means we can get the value of whatever is in the variable a and print it, which in this case is the integer 5. Awesome job. So remember, we access members of struct using the dot notation, but when we have a pointer to a struct, we need to make sure that we dereference the pointer before we can access the members. So we can dereference it in brackets and then use the dot, or we can use the stab notation, which is the shorthand. Really good work, everyone. Last question. Awesome job, everybody. Yeah, so we use the ampersand to get the address of a pointer, and we use the asterisk to declare and dereference a pointer. And we have our podium. Really good work, whoever this is. Awesome stuff. Very good job, Polite Bobcat, on your Kahoot. And to our 4th and 5th runners up as well. really good job. I'll turn my 10 hours of Kahoot music off my YouTube, which will definitely ruin my algorithm, but that's okay. Anything for the Kahoot. If you place in this Kahoot, make sure you keep track of it, and then you can get a Pokemon card from Henry on his return. But now that we've taken a little break with a Kahoot, let's get right back into our linked lists and do more inserting. Okay, let's close this. Close this here. Okay, so I did it again. I guess just chucking back to what we said we were going to do, because this diagram is also really neat. So what happens when I draw things ahead of time. Up until this point, we have learnt how to prepend, so insert at the head of our list, and append, inserting at the tail of the list. But what if I want to insert between some node, inserting at the nth position, we might say? We're going to need to figure out how to do that, because right now, we can only insert the front and the tail. That's no fun. So let's learn how to insert at the nth position of a linked list. So given some spot, we will find our current position in the list and insert a node there. So let's start with a bit of code, and then when we get to the problem solving part, we will chuck open a diagram. Okay, so hopefully we're used to it now that we're going to create a function prototype in our list.h. So function to insert at the nth position of a list. We're going to give it some parameters, and like usual, we are going to give it the head, which is a pointer to the first node in the list. We're also going to give it num, which is the node data we want to insert into the list. And what's this going to return? Well, like last time, we're going to need to be considering the different cases of our list, so let's always return the head. So a pointer to the head of the list. Okay, we should go ahead and create our function. So it's going to return a pointer to a struct node. We've called insert nth. It's going to take struct node head, what it wants to insert, and I actually forgot about it, but we probably want to pass in the position that we want to insert into our list. So let's add that to our list of parameters also. So n, which is the position we want to insert into our list at. And let's say it is 1 index. We'll get to what this means in a second when we go to implement our list. So let's copy this and take it over to list.c so we can implement it. Okay, so the first thing we always want to be thinking of when we're writing any linked list function is, what do I do when my list is empty? So let's just keep diagramming. I hope you find these helpful. If not, that's awkward, but I will keep drawing them. Because I think linked lists and diagrams are the best of friends. So we want to insert a node at the nth position, and the first thing we are thinking about is, what do we do if our list is empty? So taking a look at this, hopefully everybody can agree that once I create my node with whatever data I want in it, and it points to null, it doesn't really matter what position someone has entered that they want to insert it into, because there's only one position, right? There's no list. So we just want to make head point to new node in this case. There's no point trying to traverse the list and find a specific position if there's nothing to look through. So this is why we always need to think of the head null case. So now that we've thought through that, we can maybe write that as our first bit. So we want to create our node. So we'll have a new struct node, and that new node is going to be created using our create node function, which mallocs it and returns everything and sets everything up, and we give it the number field so it knows what data to fill in to the node. So now we have a new node that points to null. And if head equals to null, so if our list is empty, we just want to add our new node to the list and return that, right? Yeah, so we exactly just want to, instead of head pointing to null, head should now point to the new node in our list, and then we just want to return that. Hopefully makes sense. Feel free to pop any questions in the chat if it does not. But now that we've handled our base case, we then want to handle now a little bit more complicated, which is the case when we have nodes in our list and we want to find the nth position. So let's draw out a linked list that we can work off of. So we are going to have a linked list here with the nodes 5, the nodes 7, and the nodes 2. And this is going to point to null. And head obviously is going to point to the node at value 5. I have already created my node. So let's create a node with value 1, which points to null. And this is new node. And I want to insert this node, let's say at position 1. Oh, I shouldn't use white. White is yellow is not a good contrast to use. Let me use like a dark blue. So n is going to equal to 1. So I want to insert this node at the head of my list. Or after the head node of my list, sorry. So a 1 index list means that we're going to be counting each node from the list starting from 1 rather than 0. So like arrays we count from 0, a linked list you can say they are 0 indexed or 1 indexed. So this is the first node, the second node, and the third node. So if I want to insert at n equals to 1, I want to insert after the first node in my list, meaning that I want to have it like point here, and then this one point up here. Yeah? So the first thing I need to do is find this position in my list, right? So what can I use to find a position in my list? We kind of use it in insert table and print list, and it's also going to be applicable here. And I hope with the lag, by the time I say this, the answer has been put in the chat. But we're going to want to be using a current pointer. And this current pointer, we can traverse and count our position as we move along. And we can make sure that once we hit 1 less than the position, we can insert it. So, for example, if we have a current pointer that points to head initially, we can check if we're at the node before where we want to insert. So we want to do something like while some position related to current, so maybe like current position, while current position, we can do a few different things based on what we want to define. But maybe I can do while current position maybe does not equal to n, we want to move current. Because at the point where current and the position equals n, that's when we know that this node that we're currently at is the one we want to insert after. So we want our current next to be tracking the pointer that we want to update. It's a little bit confusing. Let's start writing some code and then we can draw out our code line by line as we go. And hopefully it makes a little bit more sense. So we can set a count to equal to 1. Oops, int count is going to start at 1. We can do while count does not equal to n, current equals to current next. So we want to keep going until we're at where we are. I also have not created my current. So we can do struct node current equals to head. So while our counter does not equal to the position that we want to insert after, we keep moving current along all the way, and we keep going until we reach the one we want. Then, once we reach the node that we want, we can update current next to point to the new node. However, if I just update like one of these pointers, is that right? Or should I make sure I update something else to make sure my list stays intact? Because right now, there's a lot of circles on this, which is making it a little hard to know what's the nodes, hey? Let me just delete a few of them. Cool. So right now, if I was to go ahead and insert the node with value 1 after the node with value 5, and I just updated its next pointer to point to new node, we've now overridden this pointer and we have lost all of this part of our list, right? Which is not good. So similar to how we inserted at a head and we needed to do a few different things, we need to make sure that we update new node next first to point to current next, and then we can make current point to new node to make sure that we don't lose the rest of our list. So let's go ahead and do that here. So we want to say that new node next is going to equal current next, so we don't lose the rest of our list. And then we can say that current next is going to equal to new node. So it can kind of slip between the currently tracked node and the next node. We just want to insert one in the middle there. And then when we're done, we can go ahead and return head. I also need to update my counter. We can't forget that. I always forget it, but we can't. Let's try run this, see if it works, and maybe run through it ourselves with a few different cases that we can think of to see what will happen. So let's just try and go head equals to insert nth. We want to give it the head. We want to give it some number to insert, let's say 10. And let's say we want to insert it at position 2 in our list. Let's compile our code. Hopefully it compiles. Great. And let's try and run it. Okay, so it's given us this. Let's diagram what this, like the state of this was, look at it with our code and see if it worked as we expect. So let me split screen. Oh, it's not playing nice today. Let me split screen, get a fresh diagram, because we love fresh diagrams. So up until this point, hopefully we all understood that our old functions that we had before calling insert nth meant we had a list that was 5, which points to a node with value 3, which points to a node with value 1, which pointed to the node that we insert at tail, which is -1, which then points to null. Oh, wait a minute, where am I drawing? Sorry, there we go. So this is the list that we are familiar with and what it looks like in its current state before we called our insert nth function. So then we go ahead and call insert nth. We say we want to insert a node with value 10 after position 2. So what do? We create a new node, okay? Create a new node, and our create node function sets the data and lets it point to null, and we let this be known as new node. Then we check if head equals to null, and in this case, we have nodes in our list, so head does not equal to null, so we skip the if statement, and we set up some variables. We let count equal to 1, and we set current to point to the head, first node in our list. And just as a reminder, in case anybody has forgotten, in this case, n is equal to, I think it was 2. I think that anyone has forgotten is me. Yeah, n is 2. Great. So now that we've done this, we check, is count equal to n? In this case, 1 is not equivalent to 2. So we say current equals to current next, and we move current to the next node in our list, and we increment our counter. So count now stores the value of 2. So we know we're at the second node in our list now. And we check, is count equal to n? In this case, 2 does equal to 2. So we don't need to traverse our list anymore because we have reached the point that we want to insert after in our list. So we want to make sure that we insert our node in a way that we're not going to lose all the connections. So I can't just go ahead and update current next, so this pointer, to point to the new node, because then I am going to lose this part of my list, right? So I want to make sure that before I move my current next to point to my new node, I have a way to connect my new node to the rest of the list. So to do that, we say that new node's next pointer points to the same thing as current next, because we're going to be updating what current points to, right? So we let this new node here, instead of pointing to null, we let it point to current node next. So current next is this one here, so we let new node next point to the same thing. And then now that we've done this, we know that when we connect new node into the list, we're not going to lose the rest of our list. So we can go ahead and safely say that current next is going to equal to new node. So we lose this connection here, and current next now points to our new node, and we've successfully slotted some node into the middle of our list after position 2, and we can return the head of our list. Okay, so that looks like it's working and it seems pretty simple. So I now propose the question of, actually, let's check inserting at the head one more time, and then I will propose you all a question. So let's see what happens if I insert at position 1. Yeah? So we've got this list now, and I have num equaling to 7 and n equaling to 1. So we know that our empty list case works. So now let's check inserting at the head after the head node of our list and making sure that works. So we can say we create a new node. This node has value 7 and it points to null. And it is known as new node. And we set our count to equal to 1. And we let current point to head. Okay, and then we check, does count equal to n? In this case, n already equals to count, so we don't even bother with our while loop, and we just start connecting things. So we say that new node next, so this pointer here, equals to current next. So current next is the node with value 3. So instead of pointing to null, we update this pointer to point to the value 3. And then we let current next equal to new node. So current next, being this one here, is now going to point down here. And we return head. So that seems to not cause any issues. And looking at our code line by line seems to work, which is great. But I now pose the question to you all of, what happens if I say I want to insert, 20, and my n is equal to 0? Am I ever going to be able to insert with a position of 0 into my linked list? does this function actually allow for that? Are we ever gonna hit this condition if count is equal to 0? Because we're only ever incrementing, right? So it will never work. But if I'm saying n is 0, that means that I want to insert at the head, right? So this is an edge case that we need to consider for this program and be able to insert a node at the head. So we can add a check after if head equals to null. We can do something like if n equals to 0. So if they want to insert at the head, because this will like keep going forever. So if n equals to 0, we want to insert at the head. So we can go head equals 2, and we can call out insert head function. And we can pass the number that we want to insert, which is just whatever's there in the function, and we can go ahead and return head. So if we're too far down, we might also want to do some validation. So if n is, actually maybe not even 0, maybe we can just assume that if n is less than or equal to 0. So if they put some negative number, we're just going to say that that's an insert head for the sake of this program. And then I saw something in the chat about the length of the list, validating if n is actually less than the length of the list. That's really interesting. So if I give you right now, I have n equaling to, I don't know, 6. And I want to insert a number 20 into the list at index 6. Oh wait, sorry. I need to go one more. 7. Because my linked list does have 6 elements in it now. So yeah, if I have a count that I want to insert after the 7th node in the list, and I try to do that with my current code, let's kind of see what's going to happen. Let me just make this a little cleaner. So we have our current, which points to our head at the start. And we have our count, which equals to 1. We malloc our new node with data 20, and it points to null. And then we start reaching our while loop, right? And we check, does count equal to n? In this case, no. Count is 1 and n is 7. So we say current equals to current next. So we move our current pointer to point to the next node in our list, which is the node with value 7. And we increment our counter. So count now equals to 2. And we check again, is count equal to n? No. So we go ahead and we move current to point to current next, which is the node, which is the node with value 3. Sorry, I'm trying to move it, but it didn't work. So I'm just going to rewrite it. Current is now going to point to the node with value 3, and we increment our counter. And then we say again, is count equal to n? Well, no, 3 does not equal to 7. So we want to keep looking for the node we want, and we say current equals to current next, move that along, increment our counter to store the value of 4. And we check again, is n equal to count? Well, obviously no, 7 does not equal to 4. So we keep looking because we have not found the node that we want. We move current along and increment our counter. We are now looking at the 5th node in our list. And is the 5th node the 7th node? Well, no. We have not reached where we want in our list. So as per our code, current equals current next, move it along, increment our counter to be 6, and we check, is count equal to n? Well, no, 6 does not equal 7. I feel like I'm going to get bullied online for saying that. 6 does not equal 7, so we need to keep moving. So our code says we need to move current to equal to current next, and we update our counter to from 6 to 7. And then we check n, is n equal to 7? Yes, we have finally moved as far as we want. But now I'm trying to go new node next equals to current next. Do we have a current next? Is there anything for me to connect? Have I exceeded the bounds of my list? Yes. So if I had a bigger number than 7, this would have caused an issue because we couldn't keep moving. But even now, like, we have nothing to connect. We're going to get that accessing a field via a null pointer situation. So what we can do here is we want to stop regardless of like what the count is. If the count is greater than the length of our list, so if I want to insert at the 7th position, but we only have like 6 nodes, it means the maximum count we can actually go to is the 6th one. Now we can like calculate the length of our list and do some things, or we can just go and current next does not equal to null. So stop either when you've reached the count of what you want, or if we are at the last node in our list. So stop at this node here, the -1 node, because that's the last node that we can insert after, so we can connect it up there. So let's test this. So we added something to insert at the head, so we can go insert nth head. I want to insert 6 at position, let's say -2. We'll check that that patch that we added works. And head is insert, and let's say I want to insert 7 at, will just be outrageous and say 11. And at this point, we expect to have 1, 2, 3, 4, 5, 6, 7 nodes. So we can say we also want to check that inserting after the number of nodes that we have. So this would be, we want to insert again at position, no, we want to insert a different value, sorry, 15 at position 7 to check that like actually hitting the very last node in our list works. So let's check. We expect to get a list with what? 5, 3, 1, -1, and then 2 will go somewhere in there, -2 will go at the start, and then it'll be like 7, 10, 11, 7, 15. But we'll see. Let's just check first that we don't get any errors, and then we can draw out what this program is doing. Okay, we didn't get any errors, which is a good start. And we can see that our like negative checks and our super large list, condition worked because of this condition that we added and this condition that we added for edge cases. But let's go through what this program is doing for insert nth for each of these, so we can try and understand what each part of the code is doing line by line. Okay, new diagram. And before we run any of our insert nths, we successfully have a head pointer, and that points to a node with value 5, points to a node with value 3, points to a node with value 1, points to a node with value -1, which points to null. So this is the list that we have from inserting at the head and inserting at the tail. So the first thing we do is we call insert nth with number equaling to 10 and n equaling to 2. So without even thinking about the code, I know that the second one is this one. So we expect that after this insertion, our list will be 5, points to 3, points to 10, points to 1, points to -1, right? So let's check that our code is doing that as we expect and have a look at what's going on line by line. So when we call the function, what we do is we set up our new node. So we create a node. This node has value 10 and points to null. So I'm just going to remove this so it's not in the way. And we check if head is null. In this case, our list is not empty, so we proceed to try to look at our insertions. We then check, did the NA insert be a position in the list? Well, yes, they did, because n is greater than or equal to 0, so we skip this. And we set up count equaling to 1. So we say count equals to 1. And we set up current to point to the head node in our list. And the first thing we do is check, does count equal to n? Well, no, 1 does not equal to 2. And is current next null? Well, no, we're not at the last node of our list. So we say current equals to current next. And we increment our counter by 1. And we check again. Is count equal to n? Well, yes, it is. So we don't even need to check. We don't even need to check the second condition, because we know we're at the node we want to insert and we haven't exceeded the bounds of our list. So we go ahead, we pop down here and we say new node next equals to current next. So this new node's next pointer points to current next. So let's update that. I'm just going to move this slightly closer so it doesn't have to, never mind. New node next points to current next. And we say current next points to new node. So now we've successfully made the first function call to insert 10 after the second position in our list. Cool. So now that we've got that, let's keep going to the next state of our list. I'm going to do separate lists for each one, just so you can see it. Oh, I can't scribble on this. Just so we can see it as we go after each function call. So we have 5, which points to 3, which now points to 10, because we've successfully inserted that, which points to 1, which points to -1, which points to null. I'll scroll down here. Okay. And what are we doing? We're calling insert nth with number equaling to 6 and n equaling to -2. So let's take a look at our insert nth function and what we do in this case. So again, the first thing we do is we create a new node. We let that have the data field equal to the number that we pass in. Sorry, that is not -2, it is 6. And we let it point to null. And then we say, is head equal to null? Well, in this case, head points to an entire list, so we skip that. But we do check if n is less than equal to 0. In this case, we have inputted -2, which is less than or equal to 0. So we call our insert at head function. And what does our insert at head function do? It creates another new node, which we kind of don't want to do, but I guess it doesn't really cause any problems, but it's a little bit of a bug. So we should probably fix that. And let's go ahead and, let's go ahead and move this, right? And create the node only when we need it. So we're not like double mallocing, because when you do free next week, that's going to cause some problems. So let's create the node here. We don't need to create the node here, but we are going to need to create it down here. So let's remove the double malloc, since insert at head already does it. Okay, so now continuing to insert at head, we've malloced it, we let new node next equal to head. So that being down here, instead of pointing to null, we let this point to the rest of our list. And then we say head equals to new node. So instead of pointing here, our head pointer now points to the new node in our list, prepending the node with value 6 to the front of our list. And then we return our new head, since we've updated the address that head points to. So this is why returning the head is always really important in our insert functions. Awesome. And then we return head, so we don't even look at the rest of our code. Okay, let's move on to the next thing that we do. I'm gonna, again, start a new list. And I'm gonna make my iPad landscape so it matches my computer more. Okay, so we have a head pointer, which first points to a node with value 6, which points to a node with value 5, which points to a node with value 3, a node with 10, a node with 1, and then a node with -1, which then finally points to null. We make a function call to insert nth, and insert nth says we want to insert a node with the number 7 at position 100. So what do? Let's take a look at our code and run through it and make sure it's doing what we want. So the first thing we do, we check if head is null. Head is not null in this case, so we skip this. We check is n less than or equal to 0. Do they want to insert at the head? Which we don't. So we skip that and we start setting up some variables. So we let count equal 1 and we let current point to head. And we check. Is count equal to number? Or no, 1 does not equal to 7. And are we at the tail node in our list? RE is current next equal to null. In this case, no, it's not. Current next is the node with value 5. So we say current equals to current next, and we increment our counter. And we check again, is count equal to num? No, it's not. And are we at the tail node? No, we are not. So we move current to the next node in our list, and we increment our counter. Then we check, is 3 equal to 7, or are we at the tail node in our list? Well, no, current next does not equal to null. We're pointing to a node, and 3 does not equal to 7. So we go ahead and we move current to point to current next, and we increment our counter to have the value of 4. And we check again, is 4 equal to 7? No. And is current next equaling to null? No. So we go ahead and we do the same thing. Wrong thing. My lasso. Current equals to current next, and we increment our counter. And we check again. Is count equal to num? Is 5 equal to 7? No. And is current next equal to null? Also no. The next pointer here points to a node. So we move current along. Current equals to current next, and we increment our counter. And we check, is count equal to num? No. Sorry, I wasn't meant to be comparing to 7. I was meant to be comparing to 100, but the same thing applies. Is 6 equal to 100? No, it is not. But is our current next equal to null? Yes, it is. So this condition is no longer true, meaning that we are at the end of our list, so we can't keep going. We don't have 100 nodes to find to insert after, so we just want to insert now because we found the end of our list and this is all we can do. So we go ahead and we create our new node with value of 7, which points to null, and we say new node next equals to current next. So we say new node next, this pointer here, equals to current next. So we let this, instead of pointing here, is going to point here, which in this case is also null. And then we say current next equals to new node. So we let this pointer, instead of pointing to null, so I'm just going to make this go here so it's nicer, it now points to the new node. And we've successfully inserted this node at the tail of our list. Epic. And then we have one more call to the insert nth function, which we are doing with a position of 7. So just in the interest of time, we say this is node 1, 2, 3, 4, 5, 6, 7. So once we reach the count, we would see that we meet the condition of, we meet both of these, right? So count does equal to n current next equals to null. So we do the same thing where we create the node and insert at the tail, exactly like how we did here, where we create the one, it has 15, it points to null, and instead of pointing to null, this node now points over here, and we've created our list, and I am also on top of the list, which is not very helpful to many of you. Hopefully that makes sense. We will recap it in next week's lecture. And Angela will be taking the week 8 lectures for you. Angela is one of the lovely lecturers at CSE. She teaches 1511 and 1521. So you may have seen her around, or you will see her in some of your future courses. Thank you so much for listening the last 2 days with me. Hopefully you understand a little bit about how to insert linked lists. This is going to be really handy for stage 1 of your assignment 2, which releases tomorrow. Don't stress if it doesn't make sense. We'll go over it a ton in next week's lectures and next week's Tute labs. You can also go to a help session or ask your tutors in the lab, and they will happily go through it with you. But that is all from me, and hope you all have a great evening.